So the second tool that we discussed in the previous video, Fourier series tool 2, we said that if the series has coefficients decaying fast enough, then we know that the Fourier series converges. But the question is, when do these coefficients, which we have already discovered are given by a certain formula, when do these coefficients decay as we would like? So when does this hold? This is our third tool. So in our last video, we said that if absolute value of an is less than cn squared, then the series an in theta converges uniformly. To something. We're not saying anything yet what that something is. We're just asking, does it converge to something? So let's give assumptions that actually guarantee this assumption that the decay is fast enough. So there will be two assumptions. Well, we'll need f is twice continuously differentiable. And then we also need that f is 2 pi periodic. So this is where continuity is not enough. And this is one of the challenges of Fourier series, is that things are easier when functions are very smooth or very differentiable. Often things are still true in some sense when they're less regular, but the less regular the function, the harder the statement often becomes. But under these assumptions, we exactly get this decay. And therefore, we get that the Fourier series converges to something, not necessarily the function itself. So how does this proof go? It uses an important tool that is often useful in Fourier series, namely integration by parts. We've also seen in calculus how integration by parts plays an important role with trigonometric series. It's for exactly this reason why this happens. So this expression, if you remember, is f inner product with e to the in theta, so the nth basis vectors. Okay, so if we integrate by parts, what do we get? We get a substitution. We differentiate the first term and integrate the second one. So this is f g prime. Well, if we integrate, we get 1 over in 1 over in theta times f theta, and then we subtract integral 0 to 2 pi of f prime theta times 1 over in e to the in theta. Now the first thing to observe here is that this term, you should treat n equals 0 separately. The first thing to observe here is that this term will give you 0 because it's 2 pi periodic. So periodicity gives us that the first term is 0, and therefore we're left only with the integral minus 1 over 2 pi integral from 0 to 2 pi f prime times 1 over in e to the in theta. But we can apply this again, and if we do exactly the same as before, we get 1 over 2 pi, and minus integral 1 over 2 from 0 to 2 pi of f double prime 1 over in squared e to the in theta. So what we get from this is the formula for another formula, would be minus minus, which is plus, I squared, which is minus. So minus 1 over 2 pi, integral from 0 to 2 pi, f double prime e to the in theta, d theta, and n squared. So if we want to estimate absolute value of an from above, Well, we can estimate all the terms in some specific way, namely 1 over 2 pi times 1 over n squared times integral, if we do pull in the absolute values, of f double prime. We're using the fact that absolute value on the inside is equal to the absolute value back, because the absolute value of this exponential term is 1. And we're using the fact that by pulling the absolute values inside, the integral becomes bigger. So in this step, we're using the fact that's also true for complex numbers, that the absolute value of the integral is less than or equal to the integral of the absolute value. Okay, but so let's set c is equal to 1 over 2 pi, integral from 0 to 2 pi f double prime, absolute value, and then we get that an is less than or equal to c over n squared. We're done. As long as it's twice continuously differentiable, I mean like the second derivatives. Now, as you notice that there's a pattern to this, you could repeat it more than n times. If you repeat it more than n times, what you get is an is less than c over n to the power k. And one correction to the above, well, we don't need to treat the n equals 0 case at all, because these bounds we only need for n bigger than or equal to 1. So why did we do this again? And at this point, I'll mention unrelatedly, this is a picture of Maryam Mirza Khan, the first woman fields medalist from Iran. Well, both of these were firsts, being a woman and coming from Iran. She did some phenomenal work on geometry of surfaces, but in her words now, why do we care again? Well, our ultimate goal is to say that f would be expressed as a limit of a Fourier series. But what we can conclude from this now is that if you have f that is twice continuously differentiable and 2 pi periodic, and if we use the Fourier coefficients that we would expect, so an is equal to f inner product with en, where en is e to the I in theta, then this sum converges uniformly to some function at g. We'd like to say that f is equal to g. But let's prove this claim. Well, it's fairly short. By theorem, we know that the coefficients are bounded by c over n squared when n is bigger than 1. The 0th term doesn't matter. Then by theorem, from part 2 of this Fourier series sequence, we get that the sequence of partial sums converges. Uniformly. And this is the same. Now, the remaining part of this, what we haven't yet done and what needs doing, is showing that f and g have the same Fourier coefficient. Our goal will be to show that f inner product with en equals g inner product with en for all n, where g is the sum, this is an, and this is the infinite sum of an e to the in. Now, we would hope that this fact would imply that f is equal to g. We saw a similar claim elsewhere, but we have yet to prove this for functions. This is true in Rn. In Rn, if you have orthogonal vectors, e1 through en, and if you have some v such that v and w such that they have the same inner products, inner product with pi will be the same, then those vectors would be the same. But we don't know that yet. On Monday, we will then conclude this part by showing that we do get uniqueness and we'll conclude then the proof of the convergence of Fourier series. Specifically on Monday, now let's look at this, what we have done so far. We have presented orthogonality. We've shown that if the coefficients decay fast enough, we converge. We've given a condition that gives you that coefficients converging fast enough. Now, the last part that we will need is some form of uniqueness. And all of these together, these tools will come into the proof of proving that if f is twice 2 pi periodic C2, then f is actually the sum of its Fourier series, where the Fourier coefficients are computed exactly like we would expect. And this convergence is uniform. But we still need to discuss uniqueness and the uniform convergence.